This question is given in 24 January 2025 morning shift. An electron of mass m enters in a region of uniform electric field. So there is a already uniform electric field there with an initial velocity, and the electron has some initial velocity. So basically this is your electron, and it entered in the uniform electric field with a velocity v naught in the I cap direction. Now electric field is produced in the k cap direction. Like imagine this is your k cap, like your red, these red colors are there, this is your k cap direction, and this is your electric field, this is your electric field in the minus k cap direction. Let it be downward. How much? E naught is the magnitude, and minus k cap direction downward I represented. If these electric fields are not there, then the electron might have moved straight without any deviation. Now electric field accelerates the electron, it gives the acceleration to the electron in opposite direction, It's a very good question. So the electric field is downward, so the acceleration now produces in the upward. So instead of going straight, now the electron takes the path of a parabola, projectile, like a projectile it will go. Now do you remember the projectile concept? Now it have, this is related to x axis, this is y axis. The x axis, this is your y axis. So write x component, y component separately, and you solve it. Initial velocity ux, yes, x direction velocity there, how much it is? V naught. But y direction initial velocity 0, because initially it was not there. Acceleration in the x direction 0, nothing there. But acceleration in the y direction, yes, it is there because of electric field. And we have the formula F, electric field formula, F is equal to EQ, E into Q. Q is the charge, and in the options you see charge is represented with E. Now you put that values. F is equal to MA, F is equal to M into A is equal to electric field given is E naught, charge is E. Now acceleration produced in the electron is E naught E by small m. So how much is the acceleration? E naught E by small m. Now what they want? If the de-Broglie wavelength is lambda naught initially, what is the de-Broglie wavelength after the time t? See, basically de-Broglie wavelength formula, lambda is equal to h by p. P is mv. See, simply this is a game on velocity. I want final velocity, that's it. So you have two final velocities, one is vx, general formula ux, v is equal to u plus at. See here ax is 0, so this term will be 0, so the vx will be v naught. And in the same way I can find out V Voi, correct? So how much is the V Voi? V is equal to u plus at, same formula for y direction, V is equal to u plus at. So Vy is equal to uy plus ay into t. Uy is 0, so I got Vy is equal to ay into t, simply E naught E by m into t. See, I got Vx, I got Vy, I want net velocity under root of, correct. So V is equal to under root of Vx square plus Vy square. So how much it becomes? It becomes under root of V naught square plus E naught square, small e square, t square by m square. Now substitute here. So wavelength lambda after time t is equal to h by m into under root of v naught square plus e naught square, e square, t square by m square. That velocity value we substituted here. So if you see the options, we have lambda naught. See, what is lambda naught? Lambda naught is the initial wavelength, that is h by m v naught, correct? Initial velocity v naught. So you take v naught common. So I can say lambda is equal to h by m. If I take v naught common, under root of 1 plus, okay, here I don't have v naught, so I can write it as v naught square by v naught square. Numerator V naught square I took common. So what is left? E naught square E square T square by m square V naught square. So this value is lambda naught. So I get lambda naught divided by this value, right? So where is the option? Lambda naught into 1 by divide, see this one, lambda naught divided by m square, no, this one, third option is the correct answer. Lambda naught divided by 1 plus E square E naught square T square m square V naught square is the correct answer. Thank you.